Another property we can predict from position in the periodic table is ionization energy. The ionization energy is the energy required to remove an electron from the atom in the gaseous state. So sometimes we talk about, well, sodium wants to be like neon, so it'll give up an electron. Well, that helps us to think about it, but there's still energy required to pull that electron off of sodium. It's just more willing to participate in that than something like bromine or chlorine, who's very much trying to get an extra electron. So the ionization energy to form an ion by removing an electron requires energy, and that's the ionization energy. So this trend increases as you move to the right across a period. And these are ideas of how to remember this. If we remove an electron from a group 1A element, it gives it a noble gas configuration. If we remove an electron from a group 7A element, it does not give it a noble gas configuration. In fact, it moves it away from the noble gases. So we can remember that sodium, potassium, rubidium, removing one electron from them is no big deal. Removing an electron from an element on the far right side is going to be a bigger deal. It's going to require more energy. Another way to think about that is the size of the atom decreases as we go across. And the closer the charges are, the stronger they are held, and so more energy is required to take it away. This is a very non-politically correct analogy, but I've got 6 kids and I don't care. So if you're out, the fair is going on right now. Personally, I don't like going to the fair. It seems like an awesome place to lose a child. So you go to the fair with your 5-year-old, right? And if your 5-year-old is one of those kids that I have none of, which is scared of crowds and just sticks real close to you, it's going to be hard for someone to kidnap that child, right? Because he's right close to you, and you'll see what's happening, you'll grab them. But if you have a child like my children have all been, who will just wander off and find something to do and ask people for money and to buy them snow cones and things, when they're farther away from you, it would be easier for someone to take that child, right? The electrons are like that too. The closer the electron is to the nucleus, the more energy is required to pull it off. If the electrons are far away from the nucleus, like they are in a larger atom, then it's going to be easier to remove the electron. So we see that moving down in a column, it's easier to remove electrons. The ionization energy decreases. Because we're going down, the atoms are getting larger, and it's easier to take them off. And so this is an important idea here, that ionization energy and atomic size are inversely related. So you need to remember one of them, and then remember the other one is the opposite. So if I'm going across a period, atomic radius is decreasing. That means the ionization energy is increasing. I'm going down a group, atomic radius is increasing, ionization energy is decreasing, doing the opposite. So here's the periodic table showing you the arrows. As we go across, ionization energy increases, and as we go down, it decreases. So identify the element with the higher ionization energy. Magnesium or strontium? So here's magnesium and here's strontium. Which one is going to be harder to pull an electron off of? Magnesium. Magnesium is a smaller atom. Magnesium's outermost electrons are in the 3rd energy level. Strontium's are in the 5th energy level. They're 2 levels farther out. And it's easier to pluck an electron off and make an ion. Indium or tellurium. Let's find those guys. Here's indium, and there's tellurium. Which one has the higher ionization energy? Tellurium. As we go across, ionization energy increases. Another way to think of that is these nonmetals, do they want to be positive electrons or negative electrons? The nonmetals want to be negative. Nonmetal elements form negative ions. They form negative ions by gaining electrons. Are they going to be happy about giving up an electron? No. They want to gain electrons. These are going to have higher ionization energies than these metals over here, which do form cations. These guys do not form cations. And losing an electron in ionization energy is forming a cation, positive ion. How about carbon and phosphorus? Well, going across, we would predict that phosphorus has a higher ionization energy, right? But if we're looking at the group, we would predict that phosphorus has the lower. So we have opposing trends, and so we're going to say we just really can't tell from the periodic table. How about fluorine and sulfur? Higher ionization energy will be fluorine. Going across predicts fluorine, and going down predicts fluorine to be higher. Any questions? These are trends. There are exceptions, but they're still useful. Another trend is metallic character. This is probably the easiest one to remember. So metallic character is how much like a metal is this element. Metals tend to lose electrons, and nonmetals tend to gain electrons. One way to think about this is as we move across the period, the ionization energy increases, meaning that electrons are less likely to be lost and the metallic character will be less. It also decreases as you move across, it increases as you go down. It follows the same trend as atomic size. But really all of that's pretty silly. So there's this stair-step line, and on the right side are the nonmetals. And if you forget, look at oxygen. Is oxygen a metal? No, it must be a nonmetal. How about iron? Is iron a metal? Yeah. So this side is metal, and this side is nonmetal. So pick a row like number 3. Metal, 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 semi-metal, nonmetal. These are less metallic than these guys. Metallic character decreases as you go across. Pick a column like 15. Nitrogen's a nonmetal, nonmetal, semi-metal, semi-metal, metal. As we're going down, metallic character is increasing. So if you just look at where the metals and nonmetals are, you can figure out that one. That's the same as atomic size. It's the opposite of ionization energy. So there's multiple ways to remember these things. You just have to figure out what's going to stick in your own head. Oh, I'm so tired of these examples. Let's just do the last one. Selenium or iodine? Which one is more metallic? Here's selenium, and here's iodine. Well, we can't really tell, because as we're going across, we expect, well, let's see. As we're going across, I should circle these. There was a reason I was doing that. Selenium and iodine. As we're going across, metallic character decreases, right? As we're going down, metallic character increases. Opposing trends, can't tell. Any questions? Do you want me to do the rest of them? I will. Just one? Which one? B. Silicon or tin? There's silicon and here's tin. Which is more metallic? Well, silicon is a non-metal, a semi-metal, and tin is actually in the metals. So this one is the more metallic. Oh, thank goodness, the end of chapter 9. So these are review concepts. Good to go back and look at when you're studying for an exam.